I think that the gamma ray observations in the last few years from the Fermi telescope and from Serenkov telescope like HES, MAGIC and Veritas have been showing us a lot of relevant data for assessing the origin of cosmic rays in supernova remnants. So we see a lot of gamma rays produced by the interaction of accelerated particles with in the interstellar medium, and for the first time we were able to associate accelerated very relativistic protons with supernova remnants. So I would say that the situation is almost as good as it gets for these origin of galactic cosmic rays.
Do you have anything to add?
I think it is definitely true that gamma ray observation allowed us to learn a lot of things on supernova remnants. I think that so the main problem is that we would like supernova remnants to accelerate particles from GeV, let's say, up to the NI, which is a few PeVs in particle energy. And current instruments can probe the gamma ray spectrum supernova remnants up to, let's say, a few tens of TeV, which correspond to proton energies of a few hundreds of TeV. So we are still missing 1 decade before getting to Zen. Then there is the problem that in several cases it's not clear if this gamma ray emission is hadronic or leptonic. There are some cases in which we are quite sure it is leptonic, and other cases in which we are quite sure it is hadronic. So I think that we don't have a final proof yet for that, and so we need further investigation, especially for what concerns the particles at energies close to them.
I think that apart from this problem of testing the origin of the highest energy galactic cosmic rays, another interesting question is why electrons are only about 10 to minus 2, 10 to minus 3 less than protons. And we have this information both from multi-wavelength analysis of single remnants and also in terms of the spectrum of cosmic rays that we detect at Earth. So there are no solid theoretical understanding of why there is this ratio of 10 to minus 2, 10 to minus 3. So this is still to be addressed. And always on the leptonic point of view side, I would say that the origin of galactic positrons has still to be unraveled, because probably pulsars may be possible candidates, but this at least will bring up a different source with respect to the supernova remnants for the origin of low energy cosmic rays. So there are still some work, especially probably on the lepton part of the spectrum.
Another aspect that I think needs more investigation is the propagation of cosmic rays in the galaxy, because if we concentrate only in studying sources like supernova remnants, we are missing half of the problem, because what we do there is to see the injection spectrum, more or less, and what we see something else is the spectrum after the effects of propagation in the galaxy. And I think that we know quite well the global behavior. We know that the confinement time of cosmic rays in the galaxy is a decreasing function of particle energy. And this is very solid. I think no one has doubts on this. But then, if we go into the details of the diffusion process, I mean how particles are scattered by the interstellar turbulence, I think it's something which is really very poorly understood. And so, and we have now, again, gamma rays are useful also in this respect, because we are observing, okay, not many with HES now, but let's say a few objects with molecular clouds in their vicinity. These molecular clouds emit gamma rays. So if you have a cosmic ray source and a molecular cloud nearby which emit gamma rays, you may think that the cosmic rays, that are illuminating the molecular cloud and producing the gamma rays come from the supernova remnant nearby. And so you may have a way to study the propagation of cosmic rays on small scales, I mean 100 parsec scale, which is something that was not possible to do 10 years ago.